everyone. Because of this puja session, I am unable to shoot the live session. So that's why I am coming here with a recording session of crash course, because I don't want that you may lose some of the days because of my festival. So that's why I am here available with one recorded session. Please enjoy this recorded session with same level of enthusiasm and energy that we have seen in our live classes. So we are going to solve certain number of questions that is based on the previous theories that we have and the concepts that we have studied earlier, and based on that we are going to solve one by one the questions that is I already sent in your discussion group of global. Okay, so I am taking the first question, and this is the crash course of electronic devices. The question is based on the concepts that we have used earlier. A silicon bar is doped with donor impurities. The solution of the question is not important. The important thing is that how we are analyzing the questions, because in GATE examination it is not important. It is not like that we are getting the questions of same concepts or same pattern, but if you are analyze the previous year question properly, then definitely it would be helpful for solving the new questions that we are going to get in the upcoming examinations. Either it is GATE, ISRO, BARC, everything. So if you properly analyze the previous year question, then definitely it will be very helpful to solve the questions in the 3 hours duration with the concepts on our fingertip. Otherwise, you cannot be able to solve the questions if there is some concepts that is not in your fingertip. To get the concepts in your fingertip, whatever concepts or notes that we have maintained until now can be applied to these questions in a proper way. So see the questions. We have one question from IIT Kharagpur and a silicon bar. That means I will read the questions, and one by one we have to take care of each and every point that is coming here. I will read the questions and you just watch, and you can stop the video and try to solve the question by yourself. So as we go further, the pattern of the question and the toughness of the question level will be harder and harder. Okay. So I am taking the questions. A silicon bar is doped with donor impurities. Nd is equal to 2.25 into 10 to the power 15 atoms per centimeter cube. So we are having a bar of silicon. So just I will take a bar of silicon. I am solving the question number 1. So this is a bar of silicon. That means we are taking, and we know that whatever will be the dimension of this bar, we don't have to care about this dimension right now, because the concentration I already told in my previous video, because whatever the concentration that is given in this particular any questions is always with respect to the per unit volume, and that per unit volume is nothing but the small volume which is present inside the semiconductor, which has the dimension that is 1 centimeter, 1 centimeter and 1 centimeter. So whatever concentration do you have inside this one is always given in per unit volume. So I hurt my leg, that's why sometimes I am not able to walk properly. So please take care that you should concentrate on the questions, not on how I am walking. Okay, so we should have this one. So a silicon bar is doped with donor impurities. That means we are doping the silicon bar. This is the question number 1, and we are going to dope the silicon bar with donor impurities. So just I will add some donor impurities, and donor impurities are given by N with D. This is the way by which we can write the addition of donor impurities. When we add donor impurities in a semiconductor, the resultant semiconductor will become an N-type semiconductor. Resultant semiconductor will become an N-type semiconductor. So, sir, before adding these donor impurities, what will be the type of the semiconductor? Initially, the semiconductor is intrinsic. So, initially, if you talk, the semiconductor is always an intrinsic semiconductor, and always whenever we are having questions, we can take care that there is something written for the intrinsic material also. So here the intrinsic material is silicon. So I just write here the initially it is intrinsic. So the material that we are using is nothing but silicon. So whenever silicon comes into my mind, I want to write everything about the intrinsic material that is silicon. What are the things that you can just connect with silicon? Sir, I can connect that what is the atom's density of the silicon. So how many atoms are present per unit volume? In this small volume, how many atoms are present? And that atoms, I know that you can write the atoms concentration. You can write, just because I am doing the analysis, I just write atoms density or atoms concentration. Atoms density can be written as, this is 5 into 10 to the power 22 per centimeter cube. This is the density of atoms. And if someone asks you what is the concentration of mobile charge particle, that is the electrons and the holes, that is nothing but the intrinsic concentration. So either it is electrons and holes, we are having 1.5 into 10 to the power 10 per centimeter cube. This is the concentration of electrons or holes. This is the atoms density. This is the electrons and holes density. Okay, sir. So in this way we have to run. So what are the densities that we have written here? That is none than 300 Kelvin. So it is all present at 300 Kelvin. That means at this temperature, we are having some of the electrons and some of the holes move to the conduction band, and they will become the free electrons, and the holes that is present because of the movement of bounded electrons to become a free electrons in the conduction band or interatomic space. We are having corresponding holes also in the, because whenever we are having generation, the generation always gives one electron hole pair. That's why we are having this condition. So if the doping concentration ND, this is whatever we are having here, if it is very much greater than the intrinsic concentration, then definitely we can say that the concentration of this semiconductor in terms of electrons, because we are doping ND will give free electrons easily at 300 Kelvin. So definitely if ND is very much greater than, if we write ND is very much greater than the intrinsic concentration, then if someone asks what will be the concentration of electrons in this semiconductor, this is N in N type at thermal equilibrium, that is at 300 Kelvin, then we can write whatever will be the donor atom density, that is nothing but the concentration of electrons inside this semiconductor. But you should take care that ND should be very much greater than Ni. So we can draw the same thing here. ND is equal to 2.25 into 10 to the power 15. You just write here. So I am doing the analysis just why I am taking the time, but if you listen my analysis, definitely you would have a clear idea what we have to think whenever we are having questions. So before getting everything or before getting the answer, you should think twice about the questions. Otherwise, many times what will happen? The question will take you. Okay. So definitely you should take care of the question. Otherwise, the question will take your brain and the question will dominate you. But you should dominate the question always. So this is 2.25 into 10 to the power. How much it will be? Sir, it is 10 to the power 15. So you should write here 10 to the power 15 and the unit is per centimeter cube. And if you write 2.25 10 to the power 15, whether the intrinsic concentration is given, observe here, whatever I have written that is given here, 1.5 into 10 to the power 10 per centimeter cube. And assuming the complete impurity ionization, that means whatever impurities, what is the impurities concentration? 2.25 into 10 to the power 15. This is nothing but the impurity atoms added. So this is nothing but the impurity. This is nothing but the impurity atoms added. So if this impurity atoms concentration that is added inside this one is 2.25 10 to the power 15, then 100% ionization, or we can say that complete impurity ionization, meaning that so all the impurities that has been added will get ionized. Will get ionized means they will become an ion, and if there will become an ion, definitely we are getting ion means this is Nd plus, this is the ion, and the ion concentration will become the atom concentration. If they will become an ion, then definitely it will become a plus positive ion, definitely it will give electrons to the semiconductor body. So that means how much electrons it is providing? Sir, if it is 100% ionization or complete ionization means the electrons concentration is given an N in N type at thermal equilibrium, that is 300 Kelvin. So equilibrium electron concentration they are asking. That means we are not applying any external temperature, we are not applying any external electric field, we are not applying any external light source or photon rays. In that condition, the semiconductor is said to be equilibrium, and this equilibrium word is very much important for understanding the concept behind the question. That means we cannot apply the force other than this 300 Kelvin. So 300 Kelvin is a force but we cannot increase this one. We cannot apply any electric field. We cannot apply anything else. So equilibrium, here the word equilibrium has some importance. So equilibrium word is very much important. Equilibrium. So I would write no electric field here, no increment in temperature here, and no light applied. That is nothing but the equilibrium condition. So in the same 300 Kelvin, we would have to find out what is N in N naught. So here the same sign it is written in N naught form. So N naught will become 2.25. Yes, N naught will become, because Nd plus will be equal to Nd. This is the doping atom concentration, that is Nd plus, and this will give the equal number of electrons, that will be equal to 2.25 into 10 to the power of 15. This is the electrons per unit volume per centimeter cube. Electrons per centimeter cube. So I just want to write the same thing here. So here we are getting, this is N naught, this is the electron concentration is equal to Nd, this is equal to 2.25 into 10 to the power of 15, and the unit is per centimeter cube. We don't know the dimension of the actual bar, but we know what will be the concentration of this particular volume. Very easy to understand. So, and what else we have to answer? So just watch this one. Assuming complete impurity ionization, the equilibrium electrons, we have to find out the hole's concentration also. So whenever we are having, we have to find out the hole's concentration. These holes are nothing but minority concentration. Holes are the minority, and for finding out the minority, we know that we have very powerful equation, that is nothing but the mass action law. So this mass action law, when it is applied, that is P in N naught is equal to, this is Ni square divided by, we should write Nd, Ni square, that means we know what is Ni, because it is already given in the question. If it is not given also, we know what will be the value of Ni, that is the intrinsic concentration at 300 Kelvin in the intrinsic semiconductor. So I should take care that 1.5 into 10 to the power 10, and the square of this one divided by, this is 2.25 into 10 to the power 15, then the answer would become equal to how much? Sir, this will be equal to 1 into 10 to the power 5. That is nothing but the hole's concentration per centimeter cube. So this one is written in per centimeter cube unit. So this is also similar to this. Okay, sir, this would be very easy. But the analysis that we got after getting this question is very important. So analysis is important, not solution is important right now whenever we are preparing. Okay, so if we have already prepared, then the analysis also at that time is also very important. So if you are preparing for the first time, then definitely we would have to know what will be the answer, and the answer is D. That is an electrons concentration at equilibrium condition is equal to 2.25 into 10 to the power 15, and the hole's concentration is 1 into 10 to the power 5, and the option D is correct. I know many of the student has answered already, but whatever analysis I have given, that is very important for understanding the terminology behind this. What is the meaning of equilibrium? It is, if it is given non-equilibrium, then we would have to think about what will be the next temperature above this 300 Kelvin. What will be the electric field extra applied above this 300 Kelvin? What will be the photon rays that has been applied? What is the intensity of light that is above this 300 Kelvin? That is nothing but a non-equilibrium condition. So I think I have given so much analysis on this question. I would like to move to the next question. Okay. So I am taking the next question. The next question is also from IIT Kharagpur, and what will be the question? So this is the second question I have. A silicon sample is uniformly doped with 10 to the power 16 phosphorus atoms per centimeter cube. So I will just tick marks the terminology that is very much required to understand in this particular subject. That is nothing but this word uniform, because I have seen that most of the students are not getting properly this uniform word. Uniform means the concentration is not changing within the semiconductor body with respect to distance. So if the concentration is not changing with respect to distance, there is no concentration gradient present inside the semiconductor, then the semiconductor is said to be a uniformly doped semiconductor. Can you visualize these things? Yes, we can visualize. So for visualizing the things that he's written in this particular question, that is the question number second we have. We just have to analyze properly the things. So how we can analyze, sir? Just draw the things in a similar manner that has been written in this particular questions. So for that one, I have drawn a semiconductor bar, and inside this semiconductor bar, we want to visualize the uniform concentration. So what is the uniform concentration, sir? If you are taking two distance, that is, suppose this is x1 and this is x2, and we are thinking about the concentration at this particular distance. So which type of semiconductor just we have? We are doping with phosphorus. So I know that later on we are going to dope this semiconductor with the other material. Suppose if you read this question, we are having silicon, that is the intrinsic one. Whenever intrinsic comes into our mind and we are thinking that it is at 300 Kelvin, then definitely we would have to think that what is the atom's density per centimeter cube, what is the electrons density, what is the hole density per centimeter cube at 300 Kelvin. So we know that if you are talking about silicon, then in this silicon, if it is intrinsic, and later on we are adding two different type of material. One is donor atom here and one is acceptor atom here. If you added these two material, the semiconductor would become a compensated semiconductor. In this compensated semiconductor, we understood in my conceptual part, we understood that if you are talking about compensated semiconductor, the holes and electrons both will get recombined, and we are at the result we are having those many values of the concentration of electrons and holes which is greater in terms of their doping concentration. So here I want to write that if Nd is greater than Na, then after compensating or recombination we are having, which one is greater? That means the redundant semiconductor is Nd minus Na, and this is given by Nd dash. And what is Nd dash? Nd dash is nothing but this is an N-type semiconductor, and after recombination, whatever electrons that is left behind inside this semiconductor would become the type of the semiconductor, and it will also decide the concentration of the majority charge carriers inside the semiconductor. This is the first point I want to write here. And we are having the second point also. Second point is what? If Na is greater than Nd, then what will happen? We are taking just the subtraction Na minus Nd, that is equal to Na dash, that is equal to Na dash. And the type of semiconductor is, sir, P-type semiconductor. The type of semiconductor is P-type semiconductor. So in this way, we have to think about a compensated semiconductor. And if it is silicon, then silicon, we have to think about silicon also. Sir, initially the semiconductor is made up of silicon. So why not we are taking the intrinsic concentration? I already told you, if the doping concentration, either it is Nd or Na, if it is greater than the intrinsic concentration, then we are ignoring the presence of intrinsic concentration inside the semiconductor in the presence of extrinsic material. That's why we are always separating, we are always subtracting the, for deciding the type of semiconductor, only the doped materials, not the intrinsic material. So we are have to think in that way. So it is silicon, and silicon is having the intrinsic concentration at 300 Kelvin, that is Ni is equal to N is equal to P, that is 1.5 into 10 to the power 10. Okay, and this is per centimeter cube. And just we have to think that whether we have doped with Nd or Na, if it is greater than this particular concentration, then we are going to ignore this concentration in the presence of the added concentration, added doped concentration. So in that condition, we have to think about. So we can see that the added dopant concentration, that is Nd, is 10 to the power 16, which is greater than the intrinsic concentration, which is in the order of 10 to the power 10. It is very much greater, approximately 10 to the power 6. The factor difference is there between Ni and Nd. Similarly, if you see the boron concentration, that is 2 into 10 to the power 16, which is very much greater than the intrinsic concentration, then we can ignore the presence of intrinsic concentration in the presence of this donor and acceptor concentration. So we can see from here, if this is Nd and this is Na, and we can see that Na is greater than Nd, then definitely we have taken Na is greater than Nd, then the type of the semiconductor is p-type semiconductor, and we can find out the difference between Na and Nd to decide what will be the type of semiconductor and what is the concentration left inside the semiconductor. So based on that one, we know that Na is equal to 2 into 10 to the power 16, we know that one, and this is 1 into 10 to the power 16, that the resultant semiconductor is 1 into 10 to the power 16, and which is nothing but p-type semiconductor, and the concentration, hence it is written in per centimeter cube. So from this one we have to answer. So 1 into 10 to the power 16, p-type carrier concentration of 10 to the power 16, which is present in B, and C is also p-type, but here this is wrong, and it is n-type. Because of n-type this is wrong, it is n-type. Because of n-type this is wrong. So the correct answer for this question is only B, and we are going to take the next question after this one. So we are taking the next question. The next question is third question, and in this question we are having the similar parameters, but the answers that we have to think about this question is somewhat different. Consider a silicon sample doped with Nd, that is 1 into 10 to the power 15. That means again the intrinsic semiconductor is silicon. So here we are having the intrinsic material. One by one we are marking the important points here, and we have seen that the intrinsic material is silicon. That means we know what will be the intrinsic concentration and what is the density of atoms inside this one. Doped with donor atoms, it is doped with donor atoms 1 into 10 to the power 15 per centimeter cube. This is the donor atom concentration. Assume that the intrinsic carrier concentration Ni is equal to 1.5 into 10 to the power 10, that we already know. And if the sample is additionally doped, that means if the sample is additionally doped with Na, that is acceptor atoms, then definitely we can say that this is again a compensated semiconductor, and whenever we are having compensated semiconductor, we know that the concentration which will be the greater will decide the type of semiconductor, and it will also decide the left out concentration of the charge carriers after recombination inside the semiconductor. And where we have to take the difference between these two, here we can see that Na is greater than Nd if it is compensated, and we have to subtract Na minus Nd to decide the type of the semiconductor and the concentration also. So if Na is greater than Nd, then definitely it is a p-type semiconductor. So just I will write the resultant semiconductor is a p-type semiconductor, and the resultant concentration is Na dash is equal to, this is Na minus Nd. So Na minus Nd means we have to take the difference between these two. So this is 10 to the power of 18 minus this is 10 to the power of 15. We have to take the difference. Since this is very much greater, then simply we would have to find out in this way. Suppose we are taking the next page, and we just write, this is the question number 3 we are solving, and we know that Na is greater than Nd. So the type of semiconductor is a p-type semiconductor, and the resultant concentration of acceptor atoms is here is equal to Na minus Nd, and this is equal to 10 to the power 18 minus 10 to the power of 15, and we take this is 10 to the power 18, this is 1 minus 1 divided by 10 to the power 3, and which is approximately or equal to 10 to the power 18. That means the concentration of acceptor atoms inside the silicon sample is nothing but 10 to the power 18, and this is nothing but the majority. What is this? Sir, this is the majority concentration inside the semiconductor. If this is the majority, then what will be the question that has been asked here? So the approximate number of electrons per centimeter cube. So if the acceptor atoms are the majority, then the holes are the majority charge carriers. So I would like to write here, so this is the majority, and we know that what will be the concentration of P in this p-type semiconductor at thermal equilibrium is equal to the concentration of acceptor atom Na dash And if it is okay, then we will write. If someone asked you what will be the concentration of electrons, that is, this is nothing but the minority. So I just write here we are having majority. Then if someone asked you what will be the minority, then I would like to say that minority is nothing but by using the mass action law, and we are having the mass action law is nothing but N in P at thermal equilibrium. This is given by Ni square divided by Na dash. What is Ni? It is given in the question. We don't have to think about Ni, because the gate question has framed in such a way that they are providing the constant value also, until unless they are not making any mistake. So here we are having the value of Ni. So I would like to write the value of Ni, that is 1.5 into 10 to the power 10, and the square of this one divided by, we just write here, this is 10 to the power 18. Okay, so here we are having 2.25 into 10 to the power of 20 divided by, this is 10 to the power of 18, that is equal to 225. This is the concentration per centimeter cube. Since it is minority, so first time we have seen that we are having so less concentration, 225 only. No power of 10 to the power something. There is no presence of this, because it is minority carrier concentration. So if someone asks you what we are going to put at 300 Kelvin, this is the thermal equilibrium condition. That's why we need not to think about what is the increment in temperature, because if the temperature increases, the concentration will not become a thermal equilibrium concentration. We would have to apply the temperature formula. Temperature formula means what, sir? Temperature formula means we have to count Ni again. Ni square is equal to A naught T cube e raised to minus of Eg upon Kt. We would have to apply this formula to find out the concentration. But here we have to think about only 300 Kelvin. So every part is very important. If some part will get changed, definitely we would have to think about those parts. But this question is very simple, but the analysis has taken into mind that what is written in each and every points. So I would like to write here, this is 225 only, and if it is concentration, already it is given per centimeter cube, and it is electrons. So everything is written. So just we have to put 225, and it is a numerical answer type questions. So very simple. So we are going to take the next one, that is fourth question. So this is the fourth question that we have. The resistivity of a uniformly doped n-type silicon sample is 0.5 ohm. So here we are working with the properties of the semiconductor. So what are the properties of the semiconductor, sir? Conductivity and resistivity. And in these questions, we have to think about the resistivity. So just let me take another slide, and we are solving question number 4. And in this question, we have to think about the resistivity. So just I will write resistivity. So what is resistivity? It is written by rho. And if it is for an n-type semiconductor, rho n. So resistivity formula is nothing but 1 divided by conductivity of n-type semiconductor, and conductivity of n-type semiconductor is Nd into Q into mu n if it is an n-type semiconductor. And or we can write this is 1 divided by n in n-type into Q into mu n. This is also the deciding factor for the resistivity of semiconductor and the property of the semiconductor. So if you read the question once, then we are going to get what are the things that is given. The resistivity of an uniformly doped n-type silicon sample is 0.5 ohm centimeter if the electron mobility is 1250. So resistivity is given in form of 0.5 ohm centimeter. So I just write here, this is 0.5 ohm and centimeter it is given. Okay. Then next, what we have to take care, sir, mobility is given 1250 centimeter square per. So we are writing this is 1 upon Nd, and Q is equal to 1.6 into 10 to the power of minus 19 coulomb, and mobility is given, that is 1250 centimeter square per volt second. So in this type of questions, we have to think about the units also. What are the units of different parameters given in the question? Is the unit is in the order of centimeter or meter, in MKS units, whatever will be the unit, we have to take care, and we have to maintain the units of all the parameters or variable in the same form, otherwise the answer would not match with the answer given in this particular question. So we have to think in this type. Okay, then it is given the electronic concentration is equal to 1.6 into 10 to the power minus 19 coulomb. The donor concentration ND in the sample is, so we are having 4 options, and we can see there is only one parameter that is unknown here, and to get that parameter we have to write this is ND, and this is equal to 1 divided by, we just write this is equal to 0.5, and the unit is same, ohm centimeter, it is given in ohm centimeter. Okay, then 1.6 into 10 to the power of minus 19, then this is equal to 1250, and the unit is centimeter square per volt second. So in this way we have to think. So whatever concentration that we are going to get here is nothing but the donor atom concentration, and it is again in per centimeter cube, and the answer would be, if you have done the same thing, I think the answer is 1 into 10 to the power 16. So I just write here, this is 1 into 10 to the power of 16 per centimeter cube, and the option is nothing but B. So this is about the property of semiconductor, and anything, you know the property, conductivity, resistivity, mobility, drift velocity, these are the properties, and we have so many questions based on this, and this is the very simple one that is asked in previous year GATE examination. So here we are writing that B is the correct answer. Okay, so I will take the next question, that is question number 5th. So this is another question, question number 5th, and the question is based on some graph, and the importance of graph in EDC subject is very high, because starting onwards we have seen so many graphs, and that graphs is nothing but, the first one is very important, which is the energy band diagram. Energy band diagram is nothing but a graphical plot which shows the change in the energy of electrons with respect to the interatomic distance. So this is nothing but the energy band diagram, and later on we come to some more graphs which is nothing but how the drift velocity is changing with respect to electric field, and how the mobility is also changing with respect to electric field. And we have seen that this mobility is also having important change in with respect to temperature also. So these are the graphs which gives the analysis how different parameters or properties of the semiconductor will get changed by changing the excitation, that is otherwise like electric field temperature, all other things are nothing, electric field temperature and the light rays, these are the excitation, and based on change in the excitation we are having change in the properties of the semiconductor. So I will take this question and with so much dialogues, and we have seen that a piece of silicon is doped with uniformly with phosphorus. Okay, so again we are having a piece of silicon. So piece of silicon means this is the intrinsic material, and again it is uniformly doped. That means the concentration is not changing with respect to distance. It is uniformly doped with phosphorus. So if the concentration will get changed with respect to distance, then the analysis will be of a different type, because each and every distance we are having different mobilities, different conductivity, different resistivity. So we have to take care that it is uniformly or non-uniformly doped. So we know that uniformly means there is nothing, the concentration is not going to change with respect to distance. Okay. So phosphorus means we know that this is the donor atoms, and the resultant semiconductor will become an N-type semiconductor. So I just write here, the semiconductor will become an N-type semiconductor with a doping concentration of 10 to the power 16 per centimeter cube. So if the doping concentration is 10 to the power 16 per centimeter cube, we just take that ND will become 10 to the power of 16, and the unit is per centimeter cube. The expected value of mobility versus doping concentration for silicon assuming full dopant ionization. The expected value of mobility versus doping concentration of silicon assuming full dopant ionization. Full dopant ionizations means how we can write that parameter, sir, whatever we are having the doping concentration, the same number of ions we are getting, and the same number of ions means positive, because this is donor atoms. It will easily donate 1 electrons. If it is easily donating 1 electron, this will become an ion, and equal number of electrons we are getting from here. And these electrons are nothing but the electrons per unit volume, because everything that is measured here is with respect to its volume. So the expected value of mobility versus doping concentration for silicon assuming full dopant ionization is shown below. The charge of an electron is 1.6 and the conductivity in Siemens per centimeter. So here we have to find out the conductivity. If it is conductance, then the unit will become Siemens, and if it is conductivity, the unit will become Siemens per centimeter of the silicon at 300 Kelvin is. So what is this graph representing? This graph representing that already I told in my previous lectures. What you told, sir? I told that as we increase the concentration, okay, I am checking my mic whether it is switched off or not. As we increase the concentration and the mobility is decreasing. Why? Because the mobility is nothing but the freedom of space, or easily, how easily a charge carriers are moving. So this is nothing but the velocity per unit applied electric field. In any ways, we can say the mobility is nothing but the how easily a charge carriers are moving inside a semiconductor body, or we can say that how fastly a charge carriers are moving within a semiconductor body. So that means we are having this mobility, and this mobility is gradually decreasing as the concentration is increasing. So I already sent you the questions, and we can see from that questions that it is written 1.E plus 13. The representation used that it is nothing but 10 to the power 13, 10 to the power 14, 10 to the power 15, 10 to the power 16 like this. And we are having 10 to the power 16 per centimeter cube is the concentration. So just I will take this particular part that we have to think about this one, because the concentration is 10 to the power 16. And if you draw a line vertically in 10 to the power 16, we can having two intersection point of this vertical line. One of the intersection point will give the analysis of whole, because this dotted line representing the analysis of whole, how the mobility is changing with respect to concentration, and we can have the analysis that mobility is decreasing when we increase the concentration. And here also the mobility is decreasing when we increase the concentration, because y-axis representing the mobility and x-axis representing the doping concentration. X-axis representing the doping concentration. So mobility definitely decreases because the freedom of space will get decreased. If the freedom of space will get decreased, the mobility will decrease. So based on this one, we can do the analysis. What has been asked? The conductivity. So we know the conductivity. So this is the fifth question, and we are going to analyze this fifth question in a board, and this is the answer for fourth question. Okay, adding one more, and we are going to get the fifth question. In the fifth question, what we have to think about? Sir, we have to think about the conductivity. So we just write here conductivity is equal to, this is NQ mu N. So why we are taking, sir, conductivity is NQ mu N? Because the conductivity is nothing but the addition of both the conductivity of electrons and conductivity of holes in a semiconductor. Why we are taking conductivity of electrons? To find out the answer. Okay, no problem. You can take the conductivity, total conductivity also. So what will be the total conductivity, sir? The total conductivity is NQ mu N plus we are having P in N type into Q into mu N. That means the conductivity due to holes and conductivity due to electrons, both we can take. Okay. So is their answer differ? You only can check whether we are getting different answer or same answer. Sir, how can I check? I have to get the values of all. Yes, you can get the values of all. So we know that we are having phosphorus concentration that is 10 to the power 16 and 100% ionization, that then we are getting the same number of concentration of electrons, then we are having 1.6 into 10 to the power of minus 19. Then what will be the mobility? Sir, mobility here we are having, if you extend this one for electron mobility, then we are getting it will connect with 1200 and the unit is centimeter square per volt second it is given. So I would like to write here 1200 centimeter square per volt second. This will give one answer. This will give one answer. So I have calculated already the answer, and the answer is 1.92. So the answer is 1.92. So the unit is already given, that is Siemens per centimeter inverse. So this is already given. Next one, sir, I don't want to calculate in this way. I want to calculate the whole conductivity also. So we are writing this is 10 to the power 16 into 1.6 into 10 to the power of minus 19, and the mobility is 1200. Then sir, I want to calculate this one also. Yes, you can calculate. The formula will be, this is minority mass action law, and Ni square divided by 10 to the power 16. So then we are having 1.6 into 10 to the power of minus 19, and we have to take this one as P, mu P, okay, because it is mu P. So we have to take this is as mu P, and from here we can connect with mu P also, because this line representing the mobility of force, and we can find that this is 400 centimeter square per volt second. So we just write here, this is equal to 400 centimeter square per volt second. Then again, if you calculate, then we are going to get this particular parameter. So no doubt, either we are going to do this one or this one, we are going to get the same answer, and the answer is 1.92. So whether you follow this method or this method, you want to calculate the total conductivity or the conductivity due to electrons only, the result will be the same. So don't think that we are having this particular parameter has been by heart and we are doing in this only, but you can do your personal analysis for any of the questions and think twice before answering the question. So the analysis is important, not solution is important. So you may think about in this way, because most of the book it is given that this is the answer and this is the formula that we have to use. Then why not we are thinking in this way? The result will be the same. Yes, you can think in this the way, the result will be the same. And we just put the answer here, that is equal to 1 point. Sir, this is equal to 1.92, and the unit is already given, that is Siemens per centimeter inverse. Okay. So this is about the fifth question. We are going to take the next question. Okay.